In section 4.5, we're going to be looking more at some of the growth and decay equations and kind of applying everything that we've been doing thus far in this unit. So just remembering kind of our growth and decay equation, we have this AB to the T, and we've used that earlier in this unit. And we also have a E to the RT, and we use this when it's continuously decaying or growing. And so what we're going to use for this section is we're mainly going to be using this continuously decay equation. And so for this lecture, I just want to kind of work through 4 or 5 examples here, kind of show you different options, point out key terms, and how you can kind of all put it together so that when you go into the homework and when you're studying this, you can know kind of what are key components, what are keywords, what information can you pull from a problem. Example 1 says a certain bacteria population is known to double every 90 minutes. Suppose that there is initially 80 bacteria. Write an expression that models the size of the population after T hours. Let's go back up to this decay equation and remember a couple of things. A here is going to be your initial quantity, what you're starting with. R here is your rate. T is your time, and remember E is just a number. If you were to put it in your calculator, it'd be 2 with some decimal numbers on it. So let's kind of figure out what kind of information we have. It wants us to write an expression that models the size of the population after T hours. So I'm going to go ahead and write this formula down here so we can kind of just move up from there. So the first thing that we want to do in this problem is we want to first find our R, or find our rate. Notice that initially there's 80 bacteria. It's going to double every 90 minutes, so that would be every 1.5 hours. We're going to see double the amount. So if I go in here and I plug into this equation in order to find my R, 80 is my initial value, E to the, I'm trying to find R. Then I'm going to use this information here to help me figure out that R. So I know after 1.5 hours, so that's going to be my T, 1.5, I'm double, so double the 80. Now I have everything filled in, and I have one variable left, and I can solve for that R. So I'm going to divide by 80. I get 2 equal to E to the 1.5 R. R, 1.5, 1.5 R. Multiplication is commutative, so the order doesn't matter on that. And then what am I going to do is if I want to solve this for R, I'm going to have to use those log properties. So to get rid of this E, I can ln both sides. Remember, ln and E are inverse properties of each other, and I also mentioned in the lecture, ln E kind of looks like LINE, like I could put a line through it. So I get ln2 equal to 1.5 R, and then to get R, I can just divide by 1.5. Now, this is just going to be ln of 2 over 1.5, because that's just an exact value. If you go to your calculator and type this in, it gives you a decimal value, and we want an exact value when we're working with this. So write an expression that models the size. So step 2, we're going to write the equation. So my equation would be f of t is equal to 80 e to the ln2 over 1.5 to the t. So now if you ask me any given question, after so many hours, how much bacteria would there be? I can just plug in for t, go slowly using my calculator, and then finally get what that value would be. Again, I don't want to use the rounded value of R. I want to make sure I use exact values so that I'm not rounding the whole way. The only time I want to round is in the very end of the problem when I'm stating an answer. Let's do another one. Example 2 says, the half-life of radium-226 is 1590 years. The sample contains 200 milligrams. How many milligrams will remain after 1,000 years? I want to emphasize here that when we're working with problems like this, don't just think, oh, I'm just going to pull out numbers and no words. Half-life is going to be important. Radium-226, that's just a description. 226 is not a value I'm even going to use. So let's work with our equation here. So here's my equation. First thing I'm going to do is I'm going to find R like I did in the previous problem. So I can see that it says if a sample contains 200 milligrams, So that's going to be my initial quantity. So I'm going to say 200 e to the r. And it says the half-life is 1590 years. In the previous one, we said that it doubled after a certain amount of time. Here, we're going to see that half of it will remain after this amount of years. So I'm going to plug in 1590 for t, and I'm going to say half of that 200 would remain. Now I can solve for r. So I'm going to divide both sides by 200. This cancels, and I get 1/2 equal to r to the 1590 r, excuse me, e to the 1590 r. I'm going to do the same inverse property to cancel out that e. So if I ln both sides, as long as I do it to both sides is equivalent, I get ln of 1/2 equal to, this will cancel, 1590 r, and then divide by 1590 to isolate my r. And again, that's going to be my entire r value. I'm not going to go to my calculator because I want to use an exact value. I don't want to use a rounded numerical value. So step 2, I want to write the equation. And I'm trying to point out these steps because I want you to see the steps are similar no matter the examples that are changing. So I have f of t is equal to 200 e to the ln 1/2 over 1590 to the t. I have an equation. Now in this problem, it wants to know how much will remain after 1,000 years. So step 3, I need to find the amount after 1,000 years. But now that I've done all the legwork in this and I've figured out what my equation is, it's just a matter of using my calculator. So I'm going to say 200 e to the ln of 1/2 over 1590 times 1,000. Now, be very careful when you're plugging this into a calculator. I would go in small steps as you go, because you'll notice if I just start typing stuff in, it's going to go off the screen. I might miss a parentheses. I'm going to miss an easy point to get here just calculating this. So I'm always going to start up in here. And so the first thing I'm going to start with is this complicated part up in the exponent. So order of operation says that you do parentheses first, exponent, multiply and divide, then add and subtract. So I'm not going to multiply these two. I'm going to first start up here in the exponent. So I'm going to say ln of 1/2. I'm going to hit enter. Divide it by 1590. Enter. So that's this number right here. I'm going to multiply that by 1,000. And so that gives me this exponent. And then I'm going to do my E button. Remember, your E button is right here. So I'm going to do second ln. So that gives me my E. And then down here, if you're using calculator sim line, under your negative, if your A and S button, so that takes the previous answer. And so it's going to take my previous answer, which was all of this piece, and put it to the E power times 200. So I get 129.331 milligrams. Make sure you follow the instructions and round appropriately. I will count off for not rounding correctly. So you can see, go slow, work through your problem, follow your order of operation as you go, and that'll help you the most in working this problem. But again, it's similar to example 1. We had to find our r, write our equation, in this case, plug in another amount of years. So let's do another example. Example 3. A wooden artifact from an ancient tomb contains 35% of carbon-14 that is present in living trees. How long ago to the nearest year was the artifact made? The half-life of carbon-14 is 5,730 years. Okay, so let me write my equation. So, first step, same as the other two, I want to find my R, or my rate, for this problem. So in this one, it's going to be a little bit different. I don't necessarily have a starting value, but I do have a percent of what it should be at. So when it starts, it's at 100%. If I think about 100% and I change it to a decimal, I get 1. So I'm starting at 100%, or 1, e to the r, and then it tells me that the half-life of carbon is 5,730. So that means I should be at 50%, or half of what I started at, after 5,730 years. So this all helps me to find my r. Now, 1 times e is just e to the r. having a 1 there, I can write it or not write it, but I want to emphasize how I got this. To get rid of that e, I'm going to ln both sides. And so I end up with ln of 1/2 equal to, this would cancel, 5,730r, and then divide it. So I get my r to be ln of 1/2 over 5,730. So I got my r value just like I did in the previous two problems. So step 2, write the equation. I'm trying to be redundant and repetitive when I'm saying this so you can understand the steps that you would take on any given problem. So this would be f of t is equal to e to the r, e to the r is ln of 1/2 over 5,730 t. And then it says, one artifact from an ancient tomb contains 35% of the carbon-14 that's present in living trees. How long ago was the artifact made? So in this time, we're going to be solving for t. And so 35%, remember you always want to change your percents back to a decimal. So I'm going to be looking at, when is this equal to 0.35? So a little bit different here because I'm not solving and plugging in for t like the previous problem. I'm actually going to have to solve for that t. But I'm going to use a similar inverse property here. I'm going to ln both sides. And that gives me ln of 0.35 equal to, this would cancel, ln of 1/2 over 5,730 t, and then divide. So t would be equal to this big old problem here. Okay, I'm going to go slow, kind of show you some calculator steps along the way. Remember, you have to use a scientific calculator, especially when you go to take your exam. You cannot use a graphing calculator, so make sure you're familiar with the steps and how to output this. You cannot pass this exam without using a scientific calculator. You can see for obvious reasons, we can't do ln of 0.35 or ln of 1/2 in our head. So here's what we're going to do. We're going to do ln of 1/2, divide that by 5,730. So that's this number right here. And then I'm going to do parentheses ln of 0.35, divide it by that answer I just got, and hit enter. You can see it was already going off the page just typing in answers, so you can imagine the confusion or details that would have to be there if I typed all of this in. So this gives me 8678.5, and it said round to the nearest year. So since that's a 5, I'm going to round up. So it means after 8,679 years is how old this tree is. But again, use your given information to find your R. If you're not using something in the problem, you're probably mistaken in your steps. Don't just pull random numbers. You can see we never used the number 14 in there. That was just described in the carbon. But don't forget the words that are present, such as half-life, because we did have to use that. Let's do another one. Just try and do different kinds of problems you're going to encounter. Now this one's a little bit differently because it goes back to a formula that we were previously given in another section. It says find the time required for an investment of $5,000 to grow to $7,400 at an interest rate of 7.5% per year, compounded quarterly. So the fact that it said compounded quarterly, you should have flashbacks to this equation here. No formulas will be given on exam, so make sure you understand and have those memorized of what you can work with. Then remember what you can plug in. So find the time required for investment of $5,000. Remember, the amount that you invest or borrow is your p-value or your principal. To grow to $7,400, this is my A, or how much I've accumulated. At an interest rate of 7.5%, remember you never want to use one with a percent. You always want to move it 2 places to the left. So we're going to use 0.0575 for our R. Compound it quarterly, remember that's your N, and that's your N to be 4. Go back and revisit that very first section if you need more explanation going back into those variables. So I'm going to plug in everything that I know. So I get 7,400 equal to 5,000, 1 plus 0.075 over 4 to the 4 times t. Now in this case, we're going to have to solve for this t. So make sure you follow order of operation. You combine things appropriately. First thing I'm going to do is I'm going to start with this parenthesis. I'm going to put all this together. So this gives me 7,400 equal to 5,000. I'm going to come in here and I'm going to say, okay, 0.075 divided by 4. I'm going to add 1 to it. So I get this value here, 1.01875. Now, my goal is to get that t by itself. So I'm going to first remove the 5,000. So I'm going to divide by 5,000. This cancels. I get 7,400 over 5,000 equal to this long decimal here to the 4t. Now in this one I don't have an e, and so I can't use that property, but I know if I had it as a log, I'd have that way that I can move this power out front. So I am going to ln both sides for the sake of, if I turn this into a logarithm, by that power property, I can move an exponent out front because it's a log, and then I'll be better able to solve for that exponent. So by the power property, I can move this up front, and I get ln of this equal to 4t ln of this. That makes my life better, although you might think it's more confusing, because now I can solve for this t. It's being multiplied by 4 and by this ln, so I'm going to divide by this ln. These will cancel. And I'm also going to divide by 4 so that 4 would cancel. So t is going to be equal to this value here. Now when I go in my calculator and plug this in, I want you to go slow, use your parentheses, use your details to get this out. So let me do that with you. So first thing I'm going to do is I'm working the bottom here. So I'm going to say ln 1.01875, enter, times 4, enter. So there's my denominator. Then I'm going to do ln of 7,400, divide by 5,000, divide it by that last answer I just got of my denominator, and hit enter. So I get 5.276 for t. Hopefully you're doing that along with me so you can find the steps in the order for your problem as well. Make sure your calculator is working with me as well. And then see if the answer makes sense. So it says after about 5 years, my value is going to grow from 5,000 to about 7,400, and that makes sense for a problem. Now, all this being said, we've done some more complicated problems. I want to do this last one. It does take a little bit longer, but I think it's essential now that we've done all that. In example 5, we bring up Newton's law of cooling, and it says the temperature of an object T, so this is the temperature of the object, and surrounding air with temperature T, sub S, so this is the surrounding air, will behave according to this formula, where this lowercase t is your time, A is your initial value, and K is your continuous rate of cooling. So we've seen this piece here in examples 1, 2, and 3. Now we're adding on the value of the surrounding air. And we're going to use this going into this next problem. So it says a cheesecake is taken out of the oven with an ideal internal temperature of 165 degrees Fahrenheit and is placed in a 35-degree refrigerator. After 10 minutes, the cheesecake has cooled to 150 degrees. If you must wait until the cheesecake has cooled to 70 degrees before you eat it, how long will you have to wait? Okay, so first thing we're going to do is we're going to find A, our initial quantity. So I'm going to work with this problem here. T sub t is equal to AE to the KT plus T sub S. And let's figure out what we know. First of all, it is taken out of the oven at an ideal temperature of 165 degrees. So that's my total temperature. I'm trying to find A. E is just a number. Plus, T sub S is my surrounding temperature, and it's going in a 35-degree refrigerator. So 35 is going to go over here. The first thing that I know is that K, I'm not real sure of, but T, when we start all this, our time is going to be at 0. And so although I have two variables here, you'll notice that k times 0 is 0. So it gives me e to the 0 plus 35. And anything to the 0 power is just 1, going back to Algebra 1, rules of exponents. So I just end up with 165 equal to a plus 35, and I can solve for my a. So I'm going to subtract 35 from both sides, and I get 130 equal to a. So step 1, I found my a. Step 2, we're going to find our k, which is what we had as our r in our previous problems. And in order to do this, so we used the 165, check. We used the 35 degrees. So let's use the next part. 10 minutes is at 150 degrees. So we're going to plug in the fact that at 10 minutes, it's at 150 degrees. So I'm going to say, okay, using the same formula. So that means now our total temperature is 150, that's our T sub T, is equal to A, we just figured out, E to the, I'm trying to find K. T is my time, which we said after 10 minutes, this is the temperature, plus 35, which is our refrigerator. Now I have enough information to solve for this K. So I'm going to subtract 35, follow order of operation here. And so this gives me 115 equal to 130 e to the 10k, divide by 130. So I get 115 over 130 equal to e to the 10k. And then like you saw in 1, 2, and 3, I'm going to ln both sides to get rid of that e. So this will cancel. I get ln of 115 over 130 equal to 10 to the k, because it's canceled, and then divide by 10. So now I have my k value of ln of 115 over 130 divided by 10. So I found my a, I found my k. Next step, let's put it all together and see if we can figure out our t. So step 3, now we have T sub T is equal to A is 130, E to the K, which is ln of 115 over 130 over 10 to the T plus 35. We've really found quite a few values here. So last step, it says if you wait until the cheesecake has cooled to 70 degrees, how long until, how long do you have to wait? So we're going to solve for T. So right here, we're going to plug in 70 for our T sub T. So we're going to solve that out. So we'll subtract 35. That gives me 35 equal to 130 e to the ln of 115 over 130 over 10 t, divide by 130. So I get 35 over 130 equal to e to the ln of 115 over 130 over 10 to the t. Same thing as 1, 2, and 3, and what we did over here in step 2 to get rid of this e, I'm going to have to ln both sides. So I get ln of 35 over 130 equal to, this will cancel, so I have ln of 115 over 130 divided by 10 to the t, and then divide by that large grouping to get t by itself. So it would be ln of 115 over 130 over 10. And again, let's go to our calculators together to kind of calculate this. Okay, so I'm going to say ln of 115 divided by 130, enter, and I'm going to divide that by 10. Now that is this whole piece here. And then I'm going to take ln of 35 divided by 130, and I'm going to divide it by that answer I just got. So my t gives me 107.028 for t. So it means after about 107 minutes is when this would cool off. Now looking at this problem as a whole, this definitely is more complicated, but we're in section 5 of this unit. We're putting everything together. We're applying this. We're towards the end of our college level, college algebra class. So you can imagine that things have definitely amped up here at the end. Use these examples, use these processes to help you with the homework, and if you have any questions along the way, feel free to Canvas message me.